Hello, Algebra 1. Today's video is on the subject of scientific notation. And I've never really looked into why it's called scientific notation. I know in science classes, a lot of times we use this. Um, it looks kind of complicated, but it actually mathematically provides us with an opportunity for some simplification, and I'll show you how that works as we go forward. But basically, scientific notation is numbers written in the form of c times 10 to the p, where c has to be a number greater than or equal to 1 and less than 10. So it can be 1, but it can't be 10. And this goes back to our notes on powers, where we said that we had c b to the p. So c was the coefficient, b was the base, and p was the power. And in this case, really 10 is the base. And if you go on to take some future math classes, you'll hear about things in base 10 or base 2 and logarithms and all these other things. And so hopefully you'll at least have heard that concept before. So it is some sort of a coefficient times base 10 to some power. And by rule in scientific notation, the coefficient has to be greater than or equal to 1 and less than 10. And the purpose of scientific notation is to kind of shrink down extremely large and extremely small values. So we might have something like, you do a lot of this in chemistry and physics. Like in an astrophysics class I took, we were talking about the forces of the collision of two galaxies. Those are really big numbers. And in chemistry, we talk about the size of an atom. That's a really small number. So, you might say 307,000,000,000. And that's a big number. But what we can shrink this down to, and I'll kind of talk you through how I do this, is I need a number between 1 and 10, so 3.07. And then when you multiply something by 10, really it's just moving the decimal. So if you have 3.1 times 10, that equals 31. If you have 31 times 10, that equals 310. If you have 310 times 10, that equals 3,100. So powers of 10 are just sliding the decimal. So we say, if I compare this number, that is between 1 and 10, to the actual number, how many places does the decimal need to be moved? How many powers of 10 are there? So the difference is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. The virtual decimal would be there for this 307. What is it? 3 trillion? I'm not even going to count. So since I moved the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9 places, that is a power of 10. That is the ninth power of 10. So 3.07 times 10 to the ninth. So this is standard notation, and this is scientific notation. And you can see that, actually visually, now all of a sudden that doesn't look too complicated. Going the other way, let's say I had a number of 0.00000000113. And then if I look here and I can say, well, gee, I'd want to get to 1.13. How would I do that? How would I move the decimal from here over to where it is? So that would be 1, 2, 3, 4, 5, 6, 7, 8 spaces. But now, because we have an extremely small quantity and the decimal's going the other way, that would be negative 8 powers. So positive powers of 10 are used for extremely large numbers. negative powers of 10 are used for extremely small values. One other little trick with negative powers of 10, 1, 2, 3, 4, 5, 6, 7. And this only works for the negative powers of 10, that the number of zeros between the decimal and the number is always one less than the power. So 10 to the negative 8th, you'll have 7 zeros. And it's good form to always put this leading zero before the decimal. Otherwise, that decimal sometimes gets lost in whatever you're trying to do. So be in a good habit of always putting 0 point and then listing off the zeros and those significant digits at the end of it. So 0.7 zeros, 113 is 1.13 times 10 to the negative 8. If we try going the other direction a little bit, let's take a number such as, let's do 9.36 times 10 to the negative 4th. And again, you say, well, gee, which way do I move the decimal? And there's all sorts of little mnemonics on which way to move the decimal, but I prefer to just remember negative powers are going to be tiny amounts, positive powers are going to be huge amounts. So this isn't going to be 936,000 something. This is going to be 0.000 something. So I'm going to take the decimal and I'm going to move it 1, 2, 3, 4. I'm going to fill in those little dips with my zeros. Again, I double check myself that I have, in this case, for negative power, 1 less 0. So 3 zeros for a negative 4, that's good. So my final answer in standard notation is 0.123936. So scientific notation, 9.36 times 10 to the negative 4th. Standard notation, 0.000936. Positive power, 3.67 times 10 to the 12th. That would be 3.67, and now I need a really big quantity, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I got to fill in all of those little dips. With zeros. So when you do this, depending on how many digits you have here is really going to affect how many zeros you have. So unfortunately, there's no little easy rule to double check on this one. But I happen to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So yeah, 10 zeros. So 3, 1, 2, whoops, forgot the 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's customary sometimes to put commas every 3 zeros. In different countries, they do it different ways. Sometimes you put spaces. Europe, I think sometimes they even put dots, which is really confusing. But in any case, I'm more concerned that you get the right number of zeros on there if you do standard to scientific notation conversions. The applications of this, you look at it and you say something like, all right, what is, 32 and a whole bunch of zeros, I'll leave it at that, times you're like, well, I don't know. There's all those zeros. Well, if I convert this to scientific notation, so 1, 2, 3, 4, 5, 6, 7, 3.2 times 10 to the 7th times 1, 2, 3, 4, 5, 2 times 10 to the negative 5th, then, well, gee, this isn't so hard because now I can use the power rule. 3.2 divided by 2 is going to be 1.6. When you multiply, you add the powers. So 7 plus a negative 5 is 2. So 1.6 times 10 to the times 10 to the second, which would also be 160, which is the answer. So whereas you have this very daunting looking math problem in standard notation, we can use the product rule and the power rule and the quotient rule when we use scientific notation much more easily, because you have a coefficient, a base, and a power. So all of those rules apply. The one trick with scientific notation that you'll have to work on is remember the rule that the coefficient has to be greater than or equal to 1 or less than 10. So let's say if we do, let's do a quotient rule one, where we have, what's a good example? I'm not sure what a good example of the quotient rule one is. Now let's do another product rule. And let's say we have 4 times 10 to the 5th times 3 times 10 to the 3rd. So if I do the quotient rule, 4 times 3 is 12, 5 plus 3 is 8, 12 times 10 to the 8th, but 12 violates that rule. So I have to move the decimal one more place, and that becomes 1.2 times 10 to the 9th. So I have to add that one more shift of the decimal that wasn't there before. Same way that if I take, well, this is a good quotient rule one. What if I take 2 times 10 to the negative 3 divided by 4 times 10 to the negative 5. So that's going to be 0.5, 2 over 4 is 1/2, times 10 to the second. Negative 3 minus negative 5, so negative 3 plus 5 is 10 to the second. But I've got to move that one more. So then this actually is 5 times 10 to the first, which actually is just 50. So sometimes it's simpler to put it in standard notation. But so you still have to obey those, so that creates a little bit of a shift sometimes where you've got to move the power one way or another in order to make sure that you obey that rule. That's a defined rule for scientific notation, is that your coefficient has to be somewhere between 1 and 10. Turn you loose on some practice problems of this in Delta Math. There's also some other help videos along with it. But scientific notation is extremely useful in science, and then also by being able to do some of the simpler scientific notation problems in your head, that also will make it easier when you do other math problems down the road to be able to kind of give a quick and dirty estimate of a math problem, to be able to answer the perennial question, does my answer make sense? And we'll talk a little bit more about that some days in class.